Just like Steve said, I'm an assistant professor of computer science at UC Irvine. So got my PhD from Michigan. So very nice to be somewhere warm. I feel that might be the same for many of you, maybe earlier today or yesterday. But yeah, being somewhere warm is very important. And I would never leave Southern California. So my group got a name, S-Guard, which is short for Autonomous and Smart System Guard. So our grand vision is try to secure the emerging technologies that making our whole world more autonomous and more intelligent. So the core expertise of our group at this point is on the AI systems network security, meaning the mobile, IoT, and CPS space. So basically those systems that need integrated considerations of both cyber and physical aspects. And in this particular case, as you can see, that for the title of this talk is something called cyber physical security, which means that both cyber layer and the physical layer security are very important for these cyber physical systems, especially these critical ones like cars, right? In the past, I have been working on many in these 5 sub-areas in this AI systems network security space. From like CPS AI security to the network security in different aspects, UI, user interface security, policy enforcement, access control, and also side channels. And then today, what I'm going to talk about is essentially this first part, which is the most recent interest, which we have been digging into in the past 5 years, almost, about this so-called CPS AI security. And most specifically on these 2 areas, I guess people here are mostly interesting, right? Probably these 2 very prominent technologies in this automotive and transportation space. Autonomous driving that tries to make cars drive by themselves, and also V2X, right? Vehicle to everything based this intelligent transportation systems. So I guess in this part, related to AUTOSAR, I think this is probably mostly related to the adaptive platform part. So let's see whether we can do something on that front. So for this 2 problem space, right? So I would say definitely it's very, very important, right? So as you can see from all this high-profile crashes, right? From this autonomy stack, is specifically tied to AI, right? From this Uber, from Tesla, and also from my point of view, I'm a researcher, so definitely very interested in the research aspects because in this particular case, there are many domain-specific design logic in this kind of systems that make it very different from a traditional security the problem space, like those binary analysis or like PDF parser analysis, network protocols. Right? There are many domain-specific stuff here. Very exciting. Okay, so let's get started. So I'll first talk about the autonomous driving part. So just to set the stage, right? I believe everyone here knows this, right? So I guess autonomous driving is at a very high level, right? It's just you put a lot of sensors into cars and then try to make it drive by itself. Right? So, and the sensors here are supposed to sense the physical world, right? So let's say look at the road, front cars, very importantly, right? And also those traffic related, traffic regulation related objects like traffic horns, stop signs, right? So then the sensors, once they get this information, or what they're gonna do is to go through what we can call it a autonomous AI stack, right? So a lot of decision making here, right? From perception, object detection, tracking, fusion, and then localization, right? It not only need to know where the surrounding like obstacles are, but they had to know where they are, on a map, and putting those information together, right? So we'll make a planning, make a decision for ourselves, then we just give it to control, then go back to the physical, right? Close to control. So then this is basically the system view of this autonomous driving systems, basically the latest ones. Then now we put on our security goggle, right? So okay, how can we think about the security problems that can happen in this problem space? So in this particular case, right, if you want to somehow affect the AI-based decision-making process, so there are 2 general and fundamental attack vectors. One, right, let's look at the sensors, right? So if you look at this, right, if you look at this diagram, right, so basically this AI stack, AI-based decision-making are fundamentally triggered or driven, I would say, by the sensor inputs. So if somebody can tamper with the sensor inputs, you can fundamentally change the decision-making process. And in this particular case, in the security community, actually all the sensors that I show here, like camera, radar, LiDAR, GPS, and IMU, they all have existing type vectors and have been demonstrated in the physical world. You can do something there. You can do jamming, spoofing, all these kind of things. And then if we don't attack the sensors, there's another way, right? You can go one layer forward, let's attack the physical world, right? So how about we perturb the physical world appearance and then try to then trigger some input perturbations to the AI stack, right? So in my work, I will show examples on this. We consider both of these attack vectors. So in this problem space, right? So before our group, particularly my group, started to work on this direction. So there's a famous line of work along particularly attacking the AI stack is look at the traffic sign detection, specifically stop sign. So I believe many of you have seen this kind of like similar pictures like this, right? So basically, on a stop sign surface, you put some malicious stickers on top of it, make it disappear, or you just print something that doesn't look like stop sign to human, but for machine learning, state-of-the-art ones, they see that as a stop sign, right? Spoofing and disappearing, essentially. So missing a stop sign is definitely very undesired, right? We don't want to do that, but that's not the worst case in the car setting, right? If the worst case is that you will have some safety accidents, but then if you just miss a stop sign, that doesn't directly mean that you will have a crash, right? Because there are also many aspects, many other components in the system that try to prevent the worst case. For the most importantly, in this case, like basically this obstacle detection part, right? So even if you miss stop sign, you still see other cars moving around, so we'll try to avoid them, right? So that somehow becomes very, very critical. So when my group started to work on this direction, right, we say, okay, seems that this problem space is much larger than just traffic sign. So how about we do more, be more comprehensive and also be more extensive in terms of this problem space. So basically what we did in the past 45 years is that, okay, we comprehensively look at different AI components and then try to say, okay, whether they are vulnerable, this first question. And second thing is that, are there some different kinds of vulnerabilities that can be there from the real world point of view? And then basically all these yellow boxes are from my group, and then these are mostly on the design level. Like by design, these algorithms are vulnerable because mostly on AI vulnerabilities, fundamental ones. And besides this, we also look at the implementation level problems because this is also very important, right? So in your system, it could be all good at design, even like provably to be secure by design. But this doesn't prevent those people, the developers, make mistakes when they actually implement those design in their code, right? That could be bugs. So in this case, we also look at the basically the software bugs piece of it. So most of this work, at least this one I show here, our first time at the time we look into this area pretty early. So first time to look at this particular the security problem of this particular AI components, with that problem setup, and then they are generally publishing top tier like venues across security, machine learning, and software engineering. Because there are software bugs, that's why we have software engineering conferences as well. So today, I will just give some highlights about the most important findings we have there, just to give a flavor about what we have discovered and then what kind of attacks they look like. So the first one I want to talk about is this LiDAR-based object detection. So I mean, autonomous driving cars, right? So LiDAR is one of the key features, right? Something spinning on the top, and then now they become a flash LiDAR. So we are the first in this particular case to look at the 3D object detection. Like previously, like the traffic sign work, they are 2D, right? They just put a patch, but we are looking at the 3D. So we use a attack vector called LiDAR spoofing. So what is LiDAR spoofing, right? So basically, at a very high level, right? For many of you, I'm sure many of you know LiDAR. So you send laser pulses to the surrounding environment to measure the distance. But then, if you use the time of flight of those lasers to measure distance, a fundamental vulnerability here is that attacker can shoot laser back to you, so that we can move those points around, right? So in this particular case, at high level it looks like this, shooting laser back, but then or laser shooting attack. But then more technically it's more complicated, and this is our replication. It's more physical here, right? So with this, let's see whether this video can work. So it works. So as you can see, for these points, for the in this white box, right? As you can see, they're moving from here to here, right? So these all the spoof points the attacker can inject, right? And then not just like they can inject points, But you can see that they have some certain level of control, right? They control from moving farther to closer, something like that, right? So once we find this, once we reproduce this, we find very excited, right? Because from a technical point of view, okay, we find some way to inject malicious inputs to this kind of LiDAR-based object detection. But another thing we realized is that this signal is too subtle, right? Too tiny, right? Just a few points, like usually tens of points, 20 points. It's far from directly spoofing a car, right? Which is what we want. So then what we did in the end is that we solved this problem by combining this sensor spoofing, which have some tiny perturbations, with the adversarial AI, which is known to make a DNN model, deep learning model, to be fundamentally vulnerable to the small input noises. We combine them, make the optimization, and then eventually find that we're able to go from like 0% success rate, which is actually like naive attack cannot really work, but then we get it to 75% in spoof a near front vehicle, right? So just 10 points, like 20 points, at most like 60 points, you can spoof a near front vehicle, which is typically to be like thousands of points, like 2,000 points. So, and then we find that we try a simulation, then this by just injecting this object in front of the vehicle, you can cause emergency brake or like a permanent stop, right? By putting the obstacle in front of it. So this is one nice trial, one of the early works along this line. But then we bring this to industry, we ask companies, okay, what do you think? And then they are thinking, okay, so very cool, but this is an attack on just one sensors. We typically have sensor fusion, right? So once we have fusion, it doesn't mean that it can work, right? So I mean, we can have other sources, so a single source attack does not necessarily work. Then we say, okay, let's look at fusion, right, how that works. So then in this particular work, we first study multi-sensor fusion-based perception. So what we find is that you can create some maliciously shaped 3D objects, something like broken-looking traffic cone or just a rock. Then you're able to fool both camera and LiDAR perception. So which means that even if you do diffusion, none of them can detect anything. So which can fundamentally break multi-sensor fusion. Show a demo. So basically, in this case, this is a benign case. And this is a traffic cone that we 3D printed. And then this is a benign cone. So as you can see, the surface is actually pretty smooth, very normal. And left is camera, right is LiDAR. So as you can see, this is a miniature environment in our lab. So we put this traffic cone in the middle, and then we move the sensors around and see what's going on. But then, as you can see, yeah, definitely, right, for human, that's a big red objects, right? Cone-shaped on the left, definitely an object there at least, likely to be a cone. And then on the LiDAR side, you can see some points being blocked. Yeah, sure. So then they actually didn't make it run for the state-of-the-art LiDAR detection algorithm. Then we switch to the adversarial case, right? So basically, this is adversarial traffic cone, right? So as you can see, we put in the same position, but then the difference is that, as you can see, there's something weird on the surface, right? So something like a goosebumps, right? So like some bumps. These are the malicious shape changes that we introduced. And then on the right, we basically make the similar movement. And on the right, you can see that it still blocked points, but then the points are a little bit more noisy. If you put them like really side by side, this is what we did. But then if just look at this, it's hard to tell because these are points. So as you can see, with what I just showed, right, we make the same movement, right? Same position, but in this case, even though there's still a big red object on the left, and then some points clearly being blocked, cone-shaped on the right, the state-of-the-art object detection algorithm cannot see them at all. In any of these frames, right? Then we get more confidence. Then we say, okay, how about we try this on a real car? So then this is the malicious object that we 3D printed. So this is like a rock. It will start from like a cube, like a very regular cube. But after optimization, and then we change the shape, and it becomes something like this, like a rock. So put it in the middle of this road, and then left LiDAR, right the camera. And as you can see, just like the malicious traffic cone case, right? So in this particular case, even though the signal is very clear for human eye, but then the car cannot see it at all. And then as you can see, this is actually not a very small size rock. So if you drive, you definitely want to try to avoid it as much as possible. But then in this particular case, for autonomous driving cars, they cannot see it in either camera or LiDAR, which means that even if you have fusion, no matter what kind of fusion algorithm you use, it's impossible to find it. Okay. Then well, more demos on the website, and also we open source for this one. And then we move on to say, okay, how about land detection? So which is probably the most widely deployed like level 2 autonomous driving algorithm or AI algorithm in the real world today. Let's look at that. So we're the first to look at the production land detection DNN. So we use anti-vector something like this. So because at the time, this is a land detection, right? Looking for the lands on the ground. So we need something on the surface, on the road to introduce the malicious inputs. Then we drive around Irvine, so we see, okay, there's something actually like this, which means that in this particular case, we find that this is potentially something can be introduced to do attacks, because to attack AI, you need something that's like noise-like, but also can have a strong signal. Like in this particular case, as you can see, all these kind of cases, this white stands can have arbitrary shape, while it can have, the color is actually white. In this case, you drop those pens on the ground. It's white, so it's easy to be confused with the landlines, right? Okay, so let's try it. So and then with this particular case, you can deploy it. If you are an attacker, you can deploy it using these rule patches, and then. Actually, there are some new technologies in deploying these rule patches. You can just do be adhesive, some patches can roll, and then you go there, put it there, right? Something called this adhesive rule patches, which actually make it pretty easy to deploy. Anyway, demos. So this is a attack case. So as you can see, again, we start from the in-lab setting. So this is a miniature road that we printed, and this is the road patches we put onto the ground. Looks pretty much like the previous one that we had. And then this is actually a production camera for land detection. As you can see, we simulate the driving trajectory, and then as you can see, this detected landmass are deterministically bent to the left. And then in the binary case, this system is actually pretty robust, and many of us, actually my friends, are using this every day. So it's actually pretty robust, especially at Irvine. And then in this case, attacker is able to have a good control. And again, we have more confidence, right, that we move on to the real car. But then in this case, we are trying to test, okay, if this happens, can the car actually be led to a accident? Because there are other features like AEB, right? This automatic emergency brake. So maybe you can change the steering wheel, but you won't actually trigger a crash. But in this particular case, this actually doesn't really prevent it. And then we tried 10 times, and it actually always crashed. And then in this case, this system is actually engaged. We tried 10 times, 100% crash rate, never trigger AEB. There's several cases they trigger like a warning, the beep, but then that's the most of it. And then the warning beep is actually, I remember, it's 0.7 seconds before the crash. So even if it's human, it's very hard to really take over and avoid. Again, so more demos on the website, and also we open source in this case as well. And moving on, so we talk a lot on perception. So I want to talk a little bit on the planning. So why this is interesting is because in this particular case, this is no longer DNN. So all the previous work that I talked about, right, including the traffic sign work, are attacking deep learning network, right, deep neural network. So they are vulnerable. We know they're vulnerable, so we show that, okay, there's a way you find a real-world attack vector to trigger that vulnerability and have end-to-end closed-loop effect. Plan is different because for you to enforce some safety control, especially those traffic rule conformation, you typically need a rule-based, like more traditional programming patterns. So in this case, it's more code-based or program-based instead of like learning-based, not just purely driven by data. There's the human intelligence behind it. But still, it's different, but it's vulnerable in a very similar way. So in this particular case, we find out that essentially, if you can use some common roadside objects, for example, like the roadside cardboard in this case, or like a park bike, or what is kind of traffic cone, and then you can use to attack autonomous driving. In this particular case, you are able to just put this on the roadside. Look pretty much like something you can see on the real road. This is around Irvine, and then they can trigger sharp full stop in this highway off-ramp, even if there's actually a very clear path ahead of it. In this particular case, actually we tried two industry-grade systems, and open source ones. They follow this path, and they will have a permanent stop actually at this. So basically, you have sharp stop, you could have a rear end collision, and then a full stop afterwards, which means that if you imagine this, there'll be a long queue. If you really have somebody, autonomous driving cars actually just stuck there. And we also tried on a real autonomous driving car. This R&D ones, of course, for us. So interesting thing is that for this particular this vulnerability, you don't really have to use this previous perturbations like very strange color, very strange shape. You don't need that because in this case, this is a planning vulnerability, which means that we assume that all the perception part has been done in a perfect way. But still, the vulnerability is actually in the logic, in the decision-making logic in planning, right? All the environment are correct, but then you make a wrong judgment about the environment. So in this case, it doesn't matter which object you use, as long as just two objects, right? So we can use this box, we can use corn, we can use a trash can, whatever. But as long as they are in that particular position, it will trigger this vulnerability, and in this case, cause this emergency stop. So we also have demo on our website, and also this is also open source. So basically, these are just a few highlights, and then but then one thing I want to emphasize is that even though we are the first to take a peek about the security problem in this problem space, we are not the only one now. So there are many, many more works. This is actually a new trend in the security community. So and then we also do responsible disclosure here. And then as Steve was saying that we trigger over 30 autonomous driving companies to start vulnerability investigation. And in this particular case, there are many, many other works. For example, like people say, okay, let's put this sticker on the back of the car, see what will happen. Let's use a projector to project a human figure onto the ground, and then see what will happen. And this actually make a Tesla to see a fake human. Instead of just putting a patch, right, like sticker, how about we just paint the whole car into a malicious color? It will disappear. Instead of putting the real patches, how about we just add a few dots, right? Can we make that happen? Can we make your Tesla to drive in the wrong way? And also laser shooting, so not just injecting points. Have we used the laser shooting to attack the camera? What will happen is that this will inject a greenish shade on the picture, and then this will actually cause the car to recognize a red light as a green light. Anyway, so a lot of attacks. All right, so and then in this case, this is also another camera, another Tesla attack. So essentially, they use IR light to show that there's many random objects in front of the Tesla. So we also did a survey about this space. You can see that exponential growth of papers in this area, especially in the past few years. And we also have our little community, which is this AUTOSAR workshop that we created. Get a record submission every year, and then in this year we actually turned it into a symposium, which is the Vehicle Stack Symposium that Steve was introduced. And then because it's a symposium, we have a very good people who designed the logo for us, right? Have a car ship, and then this year at San Diego was the first time, and we'll definitely do it for in the next few years. So we also have a survey, like I said earlier. So we survey the state of the art, and then categorize their trends, their status, and also recognize the gaps, research gaps there. So for those of you who want a crash course into this area, into the past 5 years, this could be a paper you can read. And I also propose a security version, the platform called PASS, platform for autonomous driving, security, and safety, PASS. Right. So in this case, we envision this to be an open, uniform, and extensible system-driven evaluation platform. So some vision there, and then we are building it now. So this is autonomous driving part. I'll just a little bit on the other side, the V2X, vehicle to everything side. So I also have a different flavor because I think if we map to like the ACES the vision, right, also align with AUTOSAR. So this is this autonomy, and then this is essentially a connectivity, right, of the transportation space. So there's many things you can enable by V2X, vehicle to everything, right? You can use the V2X technology, put OBU to the car, and then put the RSU to the infrastructure, and then you can use that to enable a lot of upper layer AI, right? For example, you can enhance the autonomous driving. You can enable smart traffic light, adjust the green light duration and order, right? You can also do something called this cooperative driving automation, right? Also standardized by SAE. So this is the Platoon, right? So in this particular case, right? But then for people who know security, right? So once we put a networking layer, right, the connectivity onto any systems, you actually open a big attack surface for attackers. In this particular case, if attacker can compromise this V2X technology, right? You compromise this OBU, RSU, any of these cyber components, your attack impact is going to propagate to all these upper AI technologies. And then in this case, one particularly realistic threat model that or attack model that I think is that the vehicle owners themselves can be malicious. They can deliberately control their OBU to broadcast fake information, right? Fake data. So this is something has been, you can compromise it physically or wirelessly or by malware. There are prior work in the security committee that show that it's possible. And also in the worst case, even if you just leave all the cyber parts alone, you can also do physical layer attack, sensor attack, right? For example, you can compromise inputs using sensor attack, like using GPS spoofing, for example, to yourself. You have full control in your car in that case. So under this threat model, so there are prior works before we go into this space. They basically mostly looking on into the Platoon system because it's a very sensitive context, right? Cars driving in a very kind of short the highway. And then what they find that is if you have data spoofing, you are able to cause collisions or have significant traffic flow instability, right? If you just mess up with messages. So we follow up on this. What we did is that we are first to design a automatic methods because all the previous work are manual. They look at the protocols and line by line, but not very scalable, especially when the code base is high. Right? Main efforts is like error prone and also hard to scale. So we divide automatic methods using model checking, basically formal methods to systematically verify the protocol, the property. And then we are able to discover 14 new design flaws that can cause stalls or decrease flow stability. And then this is kind of a snapshot of that table that we discovered. Like we discovered actually 19 vulnerabilities in total. 18 of them are new. One of them that we are able to discover has been discovered before, but in a very manual fashion, totally in the manual discovery, and we are automatic. So from here, you are able to see this vulnerability is able to cause a wide range of security implications, right? You are able to do denial service of the essentially the protocol logic. In this particular case, this is a PDP-CD. This is a certificate validation process for V2X. So if you deny of service of this, then all the V2X, those network traffic will be denied, which means that all these good features you want with V2X won't be able to work, right? Like the safety, the warnings, right? Like the blind spot, all those kind of things. So basically, there are many interesting causes here. So there are many vulnerabilities. We know there are vulnerabilities, but then why they happen, right? So there are many interesting cases. So something related to crypto, right? So they use a very short hash size. In this case, for those of you know hash design, you know the birthday paradox, right? Essentially, like in this case, if you use a very short one, it's actually very easy to crack. And then sometimes they assign unicast messages when the design actually assumes a broadcast, right? So you're able to mess up with the design process. Sometimes it's the receiver is non-responding, but then we're able to discover in a very automatic fashion. So we report this and then also receive the vulnerability acknowledgements from the IEEE 1609, basically the standardization group for the V2X. And then we also propose some mitigation solutions. They are supposed to integrate that in the next version. But there are some fundamental flaws that are more tricky, like the short hash size. So in this problem space, besides looking at the Platoon, we are actually also the first to look at the attack on the smart traffic light. So we're actually first to look at the security of the infrastructure side of V2X, right? Because these are essentially vehicle side of V2X systems. We are the first to look at the infrastructure side of V2X. So this is a US DOT intelligent traffic signal or ISIC system. Attack vector is just data spoofing in the V2X data plane. So we find that because some of the actually traffic control algorithm design flaws, even one single attack vehicle in one intersection are able to cause big traffic jams. So in this particular case, we actually go to this intersection. This is of course simulation, but then we cannot really control intersection to do experiments. But then we try our best to go to that intersection and then videotape the traffic to make the simulation very realistic. And we found that it's actually able to cause a massive traffic jam. Some demo here. And then on the defense side, we also perform defense designs on both the infrastructure side and also the vehicle side. They have pros and cons. So if on the vehicle side, it's harder to deploy, hard to force every vehicle to deploy, but maybe that's something AUTOSAR can help. But then on the infrastructure side, you cannot fundamentally solve the problem because the root cause is the vehicle side. So just to conclude, so hopefully from this talk, you're able to see that so we are actively trying to do something in this AI system network security. In general, in the computer systems like arena, but then we are in the past 5 years and also in the foreseeable future, we are going to focus on the CPS AI security, mostly in the autonomous driving and also transportation context. So we have our website with all these works, not just this, but many, many others put together. So from my point of view, I believe this is just an early stage about this problem space, right? So as you can see, we are mostly focusing on the attack side, but then we definitely want to do defenses, right? So how can we go there? So definitely need at least another 5 years to actually solve these problems, mostly. And then to facilitate community building, so Steve also introduced, I co-founded this very cool symposium. Definitely check it out, called VehicleSec. So just earlier this year, this is the first time. It's co-located with NDSS. Essentially, NDSS is a top-tier security conference, so we want to co-locate with each other to benefit. And also, we are both under ISOC, Internet Society, and we love San Diego. Also good for me. And then it's building upon this four-year AUTOSAR workshop that we built since 2019. So we have a Twitter account. So just if you want it, just stay tuned about what will happen. So besides this, I also co-created DEF CON's first autonomous driving hacking competition. It's another very fun thing. So basically what we did is that, so we create a competition, and then this in the simulation. It's easier for other people to participate. Then in this particular case, we create different kind of challenges for them to solve, right? For them to hack, right? And then for example, you can, it's actually on both attack and defense side. For example, you're able to challenge you to design an attack that can make a autonomous driving car crash, or we challenge you to do a defense, right? If there's some attack there, so can you actually build a secure control algorithm? And then we did it the second time last year. So DEF CON is every year in Vegas, fun place to go. And then this is the second time, and then this is the on-site view, and then this is scoreboard, and then we also have a Twitter if you want to take a look at. So besides this, I also served on the NIST focus group on the AI test standards and metric development. So so my role is more on the security side, how to contribute the security metrics. And then last but not least, I want to just thank all my sponsors, and then definitely all this my contacts. Contact me if you are interested. Definitely happy to chat more and then form collaborations with AUTOSAR, because in this case, I'm interested to see how AUTOSAR can help in this particular case with this AI, or more in general, data plane attacks, right? So because AUTOSAR, if you look at the ECU attacks, they're mostly on the control plane, right? We send commands in the canvas, but these are more data plane. So the control, the protocols are all good. We don't attack those part, but we inject fake data, run data in sensor plane or network plane. So is there some way to define standards or define interfaces, mostly probably in the adaptive the platform, to actually help future adaptive application developers to better secure, defend against these kind of systems. Okay, so with that, I will just leave it there. And then, yeah, so happy to take questions. Thank you.